Hello everybody, I am Eric Tschetter, lead architect at Metamarkets. This is Danny Yuan, I'm co-presenting with. He's cloud systems architect at Netflix. And we're going to talk to you today about using Druid for interactive queries on real-time data. The structure of the talk is basically I'm going to start out discussing a little bit about what is real-time. Word gets used a lot. I'm going to try and provide some definition on it. I'm going to hand it off to Danny. He's going to talk about Netflix, how they're using Druid to get insights in real time and all of that stuff. And then I'm going to go into a little bit about how Druid does real time, what the nodes look like, and the availability story and kind of best practices or configuration management, deployment configuration around how you can set up a real-time cluster. And so with that said, real time, what, huh? I'm sure everybody has been walking around the expo today and the other days, and they see every booth out there has the word real time on it. And everyone is talking about real time this, real time that. What is real time? Well, real time, it's kind of the new cloud. I think a few years ago, Larry Ellison was famously quoted as saying that cloud is everything because we constantly redefine cloud to mean whatever we want it to mean. And real-time is kind of going in that same direction. We've got real-time everywhere. And in general, I think, though, you can distill real-time down to one of two things. And when you're talking about systems and doing real-time, one is the rate of query return. It's how fast you're getting answers back when you ask your question to your system. And two, it's the latency, the amount of time it takes from the event to occur until it can be reflected in an answer from your system. And so there's data ingestion, there's real-time data ingestion, and there's real-time querying. And in general, talking about real-time data ingestion, we have, for these, I'm going to call, or real-time queries, I'm going to call these interactive queries, just so that there's no confusion between what real-time means. I use real-time to mean data ingestion, and on the query side, I talk about interactive queries to mean fast queries that give you results back. And at Metamarkets, we've been providing this service to our customers for kind of real-time querying, real-time data ingestion, interactive queries, real-time data ingestion for a while, and we've learned some things about what real-time actually means to people. And you can see on the little spectrum there, this is the result that people have when they're issuing queries and getting their results back. And you see in the 0 to 5 second range, people are happy. When you get results back in 0 to 5 seconds, you're happy, you can ask another question, you can keep going, you can interact with your system and your data. Once it's over about a minute, then you know, well, I'm not going to get my answer back real quick. I'm just going to go grab a cup of coffee, sit back, relax, and I'll come back and the answer will be there eventually. But there's this sweet spot between 5 seconds and a minute where it's not long enough that you can ignore it, go off and get a cup of coffee, but it's just so long enough that you sit there constantly waiting for the results to come back. You're like, give me my results. Okay, come on, give me my results. And then you finally get it, and then you change your query, or you do something, and you wait again. And then you change it again, and you wait again. And all of a sudden, you've spent 20 minutes doing queries where 15 minutes of that is actually waiting, and 5 minutes of it is actually querying. And this is actually the worst point to be in the spectrum of things, because it's the one that gets people the most annoyed. On the real-time ingestion side, the real-time data or real-time data ingestion, we've noticed a similar spectrum, actually. When it takes about 0 to 15 seconds from the event generation to it being reflected in your system, you're happy. You're happy. When you look at your data, you believe it's up to date, you believe it's telling you what's going on right now, and everything's wonderful. Once it's over 15 minutes old, you're sad, you're sleepy, you know, well, this is out of date. You can still make statements on it, you can still come to conclusions, but you know it's out of date. And 15 minutes versus 30 minutes versus an hour versus 2 hours, it's all still out of date. There is a difference. 15 minutes is definitely better than 2 hours, but at the end of the day, the way you're thinking about the data you're looking at is that it's old and it's out of date. And once again, there's a sweet spot in the middle in the 15 seconds to 15-minute range where you got it down to 15 minutes, and you're like, well, can't we do it faster? Can't we get it to 10 minutes? And then you get it to 10 minutes, and you're like, can't we do it faster? And you get it to 5 minutes, and you're like, can't we do it faster? And you're in this constant push to try to pull it down. And so we've learned that if it's over 15 minutes, it's over 15 minutes. Don't worry about it. If you're going for under 15 minutes, you need to jump the gap and hit the 0 to 15 second point, because otherwise you're just constantly going to be frustrated with the delays and not knowing exactly, am I looking at what's going on right now, or am I not looking at what's going on right now? Is this actually delayed, or is this not? And so there's some ideas around what is real time, what it means, the ways to think about it, and ways to think about whether or not you need it. With that said, I'm going to hand it over to Danny, who's going to talk about Druid in use at Netflix.
Thanks, Eric.
Yep.
Hi, everyone. Thanks for coming. So what I'm going to talk about is what we just released and what we have been building for the past few years, the real-time data insights in Netflix. Right? First of all, who am I? My name is Danny Yuan. I'm a member of the platform engineering team. I work on this very large-scale data infrastructure. I also built and operated the Netflix Cloud Crypto Service, which pretty much manages all the keys we use in the cloud, which translates to billions of requests per day. And I also work with Jay Bay, who also happens to sit here, welcome your questions later, on this real-time querying data stuff. Okay. And for the use cases, what I'm going to cover, one is the real-time operational metrics, and the other one is the business or product insights. For example, who would know that 90210 is the #1 search query by Canadians in the past half an hour or so? Okay, so before I start, I need to do a little bit of introduction on what we mean by log events. Log events are really just parsed logs. They are parsed into these key value pairs. It's a set of field name and field value, and the value can be anything that can be serialized into string eventually. Okay, and then this is our common architecture. We have tens of thousands of servers grouped into hundreds of applications. They come and go all the time, but they all send data, and there's no limit. There's no constraint or official policies. They can send as much log they want to these highly reliable collectors, and the collectors then collects the data and then filters them, transform them, and then dispatch them into different destinations. And also those destinations are really dynamically configurable because we introduced this newly dynamic plugin infrastructure. So why is it interesting? Why is log interesting? As Adrian used to say, Netflix is a log-generating company that also happens to stream movies. Let me put that into perspective. So 1.5 million messages, this is what we get during the peak hours every second. And on average a day, we got about 70 billion messages every day, and the number is also growing. So we get this much amount of, vast amount of data, then there must be some value we need to take advantage of. Right? So the challenge here is really to make sense of billions of messages or events. And it's not like we don't have tools. We do have tools. We have those collaborative projects. Like we have this real-time dashboards that our API teams built. And then we have this really powerful monitoring systems that monitors millions of metrics every second. And we also have this CSI tool that applies a number of machine learning algorithms that finds the correlations or trends among the monitored metrics. And of course, our DSC team, they build like Hive database. They actually build a bunch of really powerful tools to make using Hive really easy. And we even have a visualization tool that visualizes the Hive query results, also built by DSC team. And we also have this live search tool that searches live instances. We have, let's say, you pick your servers, and then you fill in your search options just as you're using grep, and then you get your results back, including visualizations, right? So besides that, we also have this log summary tool, which generates a log summary telling us which applications generates most number of logs in the past half an hour. But something's missing here, right? For example, this guy, it has a half-hour delay. It's a summarization. It's a static snapshot. We cannot drill down on these things. Then there must be something we want. And to summarize what's missing, I'd say it's interactive exploration. You really want to we don't want to get the data when the data is ready. We want to get the data when the data is produced. And we want to interactively query our data, especially when the data, we don't even know what kind of query it is. Right? We just want to refine our queries along the way, but also rapidly. Okay? And so that means we want to get results back in seconds. Like here's one example. This is the same log summary we built to replace the one that I just showed you. But if you notice the timestamp on the right, left-hand side, it's not 30 minutes. It's 10 seconds. Right? Wouldn't you want that? And then also, because Druid takes over the task of aggregating data, we can actually build links. You can click on those fields here, and then you can get to the individual data points by going to a search engine. It's all linked. Right? And also, maybe that is not interesting because log summaries is rare, but let's say this new example. We have hundreds of devices. They all log all their activities to us. So that translates to 150K messages per second. But what if I want to see how many users have started streaming in the, let's say, last 10 minutes? How can we do that? I click a button, and then we get nice visualization out of it. And this is literally how long it takes to grab all the data from the globe, aggregate it, visualize it, and print it on the screen. Okay. But if it's just a nice visualization, it's not that interesting, right? So we also want to query data along different dimensions. This is where interactivity comes in. And you can see here, we have only a few dots. That's only because we are querying about errors. We want to find out in the past 10, is that 10 seconds? In the past 10 minutes, how many errors happened for only the PC players and only happens to event start play. And that's a relief, because there's only spotted occurrences. And this is another example. So in the past 5 hours, I want to find how many users have started watching any episode of the House of Cards, and you get that. Right, so you can see that with the right tools, we can actually turn huge amount of data into something useful and extract the inside of the information. Okay, and also we want to discover outstanding data. Here's one example. Let's say I got alert, HTTP 500, lots of them. What do I do? Then we go to our UI, and then we say we capture all the request traces. Then we just select the request trace, and then specify the time period, which is 5 minutes. And then we say we want to ask the question, which device models for which service points have generated this kind of error? Then we run the query. Of course, we need to filter the results only by status code 500. And then we run it. It takes 2 seconds. You get your top 5 contenders. And you know the #1 problem is the Netflix, Xbox for the list titles. And another thing is we want to see trends over time, right? Not just top-end summaries, but trends. And not just trends for a single time period, but the trends over different time periods for the same data points. So I can see what's changed now compared to what was, let's say, a day ago. And this is what you get. So we can even apply post-aggregation on our data, filter that for only application and CCP, which is our Netflix control protocol. And then we get this. So the blue line is what is happening right now, and the red line was what was happening a day ago. So you can see the blue line is much better, maybe because we fixed some problems. And the third one is the data distributions. Average can be deceiving most of the time, right? We got a lot of alerts, even though our average is fabulous. So we want to see 99 percentile. We want to see 95 percentile. Percentile is much better. And this is what we get. Of course, it's only like 4 percentiles, but really we can dynamically justify the number of buckets, the histogram things, right? Okay, that's the use cases we have. I want to also share some technical challenges when we do like implement this solution. Number one is to minimize programming effort. Make no mistake, Netflix instrument their code a lot. Actually, we instrument our code to death, but we don't want to instrument our code more just for a nascent system. Right? So we really want to make sure that we don't have to do anything extra, and then we get this thing for free. So 2 things happened, or 2 things helped. One is the homogeneous architecture, which is kind of no-brainer, but I'll explain that anyway. The other one is to separating the producing logs from consuming logs, which is a natural consequence of these requirements. Right. So here is our data pipeline. We have only a single data pipeline. And what's more is we have common build framework, we have common deployment environment, and we also have common platform libraries. So everything is shared. All we need to do is to introduce this new functionality, and we hide all the logics of sending the log behind the scenes. All user needs to do is to construct their event and call one9, the log manager.log event. And this log event gets sent over this pipeline into log collectors. And the second one is, since we don't want the user to do anything, right, like minimum programming effort, so we have to push all the logic to the backend on the collector side. And this is it. So once the log collector gets the data, then it gets the log dispatcher, it kicks in, and it actually performs 3 important functionalities. One is to filter logs, because not all the logs are worth it, and also transforms log, and eventually sends logs into different destinations. So with this simple architecture, then it's very easy for us to introduce new functionalities, because we don't have to touch all the applications. All we need to do is to touch our log collectors, which is much small, like compared to all the other machines. Okay. The other one is not all logs are worth processing. If you have to store all your logs, then the number is too huge. And sometimes some data has an expiration date, and some data has value only if you get to it in the past, let's say, 10 minutes. Right? Then how do we do that? Then we turn on this dynamic filtering. We inject runtime code, and the runtime code can do something interesting. So basically, we treat any object as a graph. And since it's a graph, then any data can be accessed by a path. We use XPath. So we introduce this infix like a mini language. For example, here, if I have a request object, then I can say, give me the log data only if the response status code is 200, 204, or 206, and the request URL matches the get title. Then thousands of messages flows through this filter, and only the matching ones will be indexed. The next one is the JSON payload is tedious. You don't expect, and the solution is to build a parser to really hide this complexity away. Let me show you an example. This is what you get if you use the API directly. You get 41 lines just to do one simple thing. What is that? This. You calculate your average time and translate the average time from microsecond to millisecond. Yet, you get this, right? Because this essentially is an abstract syntax tree in the JSON format. So we built this parser on the front, on the UI that translates this thing into JSON payload and greatly simplifies our work. Another one is managing data sources can be hairy, especially when the system is new. You have to tear down data sources. You have to update schemas. You may need to tune your systems. You need to restart your clusters. Everything we do in the very beginning might impact other systems. Right? So Jay actually built this great cell-like deployment. Everything is isolated. We put our metadata into Eureka to manage our ASGs, and then we put dynamic configurations into this Arceus, and then the deployment is managed by Asgard. By the way, they're all open sourced, so you're welcome to check that out on our GitHub repository. And each cluster has its own persistent queues. Each cluster has its own real-time indexing server. They all tap into the same data pipeline. So if I want to add a new data source, easy. I add a new deployment. And because the deployment is managed by Asgard, it's just a few clicks away. And then if we have any configuration changes, we update the configuration using a web UI on the RKS. Okay? And then also we need to integrate with Netflix infrastructures. Maybe this is not news. If we build a system, we operate it. Right? We don't want to get a PagerDuty call at 2 a.m. in the morning. So we have to make sure every operation is transparent to us. If there's something wrong, then we know beforehand. That means we need to integrate with our infrastructure because our infrastructure provides all kinds of support, especially monitoring support. And here's one example. This is our monitoring graph. And you can see this is for one data source. They are error log messages. And during a peak outage, actually 500 megabytes of data flows through our pipeline. If we don't have this integration, we're blind. And there's no way for us to know that we have 2 drops and a spike. Right, so on the Netflix side, we integrated Kafka with Netflix Cloud. Kafka didn't have this built-in monitoring, so we changed their code to do that. And we also built operational supports around it. And also, we introduced this real-time plugin onto Netflix data pipeline so that we can do dynamic filtering and transformation. And also user configurable event filtering, as I talked about. And on the Druid side, we integrated Druid with this Netflix monitoring system. Druid has this dependency injection, I wouldn't call it framework, but let's say support, that it has this emitter, and we have our servo. All we need to do is to wrap our servo into a new emitter and just inject that into Druid system, and then we get our own monitoring data streaming back to our own monitoring system. And also the integration with Netflix platform library. Again, Druid has this dependency injection support, so we can just inject our data relatively easily. And then also handling of Zookeeper session interruption so that our system becomes more robust and fault tolerant. And also we tune this sharding spec for linear scalability because we don't put a constraint on how many log lines that our system can send to the collector. Right? So we want to make sure if the traffic grows, then our cluster grows accordingly. And finally, the open source plan. We build our solutions on top of the numerous or enumerous open source packages. So we want to contribute back to the community as well. So we are going to open source the event filtering, the collectors, the collector agent, and also this explorer I showed you guys. And so now I'm done, and then it's Eric's turn. Thank you. This is yours. All right.
Awesome. Thank you, Danny. I love every time I hear about how they're using Druid. I love it because it makes me happy inside. I don't know. But anyway, I'm going to go ahead and move on then. So Danny spoke about how Netflix has been able to use Druid to get insights into their data. And so now I'm going to tell you about how it actually does real time, what that looks like. For those of you who don't know what Druid is, here's a real quick slide. We are a distributed columnar analytical data store. We went open source in October of last year. Actually, we announced it at Strata, New York. We did a talk there kind of discussing things. And Druid supports both the real-time data ingestion and interactive querying that I was speaking about earlier. You can see the code on GitHub, and you can read our blog at metamarkets.com/druid. On the blog page, there is a video of the Strata talk from New York that goes into a lot more detail on the overall architecture of the system as well. So if you're still curious after what I've said today, you can go there, listen to that, and hopefully it will answer your questions. But moving on to real-time specifically, there's 2 aspects of real-time that I mentioned that need to be supported by a system. And interactive queries, We have them. I'm going to hand wave this away and say we have them. We discuss kind of how they work and all of that on our blog and in the talk on the website. And so if you're interested in how that works and why we do interactive queries, please check those out. What I'm going to talk about today is actually how we minimize the data ingestion latency. And so this is our real-time nodes. So what was that? Yeah, and specifically I'm going to talk about how we do it, some things to think about when dealing with availability, and kind of some best practices around deployment. The how, the main driving concern, the main idea behind how we handle real-time data ingestion is separation of concerns. We separate out the ingestion of real-time data and querying of that data from the concerns of querying historical, long-lived, static data sets. And we divide those up into two separate kind of systems within the same Druid cluster. And so what do I mean by that? This is an image, kind of a very high-level image of what a Druid cluster might look like. You have in the top, for you guys, the top left, you have the stream coming in, the blue squares. It's the streams of data coming into the real-time nodes. The real-time nodes bring in the data. They effectively buffer it, and I'll get into that a little bit more in the next coming slides. But they bring in the data, and then every once in a while they hand it off to what we call historical nodes. And the historical nodes hold the old historical data sets and make that available for querying. And then in front of all of these nodes, we have these brokers. And the brokers are the things that you actually query. You query a broker, it understands where the data is located and routes the request based on who it needs to talk to answer your query. And so that's the basic structure. And by getting this separation, it's clear that the real-time nodes only deal with, one, the incoming stream, and two, the queries against the data that they have. And given that they're handing data off regularly, that data size, the amount of data that they have to deal with queries against can be limited and kept down so that these nodes don't get overworked. And specifically how they work themselves, this is kind of this is a view of the flow of data through one of the real-time nodes. What they do is we have the stream coming in, and there's one event, and then two events, and then three events hitting the real-time node. And they just buffer up inside that real-time node. And then on a periodic cycle, we go and we flush what's been buffered out to disk. And this is local disk on the machine. And then we go back and we buffer up more stuff. And then after some time, we flush that to disk again. And then we buffer more stuff, and then we flush it to disk. All the while, the system, the real-time node, takes care of running queries against both the stuff that's being buffered right now and the stuff that's been flushed to disk. And then at another time bound, it takes everything that it's flushed to disk and merges it together into one large, what we call segment, and hands that off to what's listed as deep storage. Basically, deep storage is the handoff point for data between the real-time nodes and the historical nodes. And so it buffers it up and hands it off. And so this is kind of how it works and how it manages the ingestion of the data and kind of persistence around it. And so then there's questions about availability. How do we handle availability in this situation? And specifically, availability deals with your failure scenarios. And the failure scenarios, the two big ones that we care about are losing the process and losing the disk. And so going back to this image, if we lose the process, then what happens is we still have everything that's on disk. All we have to do is bring the process back up, and then it can load back up what it's seen from disk, go back to the message bus, get the messages, buffer them up, and just keep going. And so we don't actually lose data in this scenario as long as that disk stays there. Now let's say we lose the process and we lose the disk. Now in this scenario, we've just lost everything that we've persisted to local disk for the time. And so in this scenario, if this is our only copy of that data, then that data will not make it to deep storage. We've effectively lost it. And so how can you guard against this sort of data loss? What can you do to stop yourself from losing data in this situation? And basically, it all falls back to the features of your message bus. How are you delivering messages in real time to the system itself? And the key features that you care about are message committing, basically being able to commit batches of messages. You want to be able to replay messages. And you also want to be able to consume the same feed multiple times. You basically want to be able to replicate the feed onto multiple different machines. And so, talking about commitment, we've got our message bus and we've got our real-time node. Basically, the way we use commitment in Druid is when the real-time node, when it's buffering messages up, it just buffers it up. It doesn't send anything back to the message bus. As soon as it persists to disk, then it says, OK, I'm going to commit this back to the message bus and say, all the messages you just sent me, I've now processed and they're done, they're on disk. And so that's one level of making sure that the data has been processed. And this is actually how we recover from losing the process itself, is because when we lose the process, we lose everything that's been in memory. Everything that's in memory hasn't been committed back to Kafka is what we currently use. Everything that's in memory hasn't been committed back to Kafka. So when the process comes back up, it reads back from Kafka and rereads the stuff that had been buffered in memory and just gets to keep going. Then there's the replication. And this is fairly straightforward. If you have the ability to send the same messages to multiple different machines, well then, if you lose one machine completely, you lose the disk, you lose everything, you still have another machine that's processing that data, that has the data, that can run queries against it and handle all of that. And for setting this up in Druid is simply a deployment time concern. All you do is configure multiple machines to process the same data, and now you have multiple machines processing the same data. There's nothing you have to do on the query side to know that you might be talking to replicas or anything like that. So yeah, moving on to, or summarizing the best practices, it comes back to the event delivery mechanism. The 3 points that I mentioned Kafka provides for us, we use them to provide availability. And I'm going to keep going so we have some time for Q&A here. Next up, one other thing that we recommend doing, we do this at Metamarkets when we're processing stuff, is you want to cover your bases with batch processing. There are certain things, certain artifacts introduced by real-time event delivery mechanisms. A lot of real-time mechanisms, like Kafka is one of them, it guarantees read at least once semantics. And so due to how Kafka works, you can get duplicate messages. You can read the same event multiple times. And a lot of high throughput real-time systems have this, not necessarily, it's not a limitation, it's not a problem, it's just that's part of their semantics. That's how they work. And so in order to deal with that, you can get duplicates. You can also, there's a certain amount of business logic and processing and data cleansing that sometimes you just have to wait to know the right way to do it. You have to wait for some other data set to come in to know how you should cleanse your data, how you should change it around. And so you can't really make those decisions in real time. But you still want visibility into what's going on in real time. You want to see as much as you can in real time and are willing to wait a little bit for the business logic to be applied. And in these cases, what you want to do is take your real-time stream and you pull that into your real-time nodes with Druid. At the same time, you can tee it off into archival storage, something like S3, something like HDFS, and have it there just forevers. And from that point on, you can use batch processing to go back and deduplicate. You can also go back and apply business logic and adjust things and basically regenerate the data for the past that you ingested via real time and push that into Druid. And Druid is set up to allow you to swap in new updated data in an atomic fashion without the query end having to know anything about it. You just push in the data, it handles it behind the scenes, and you don't worry about it. And so with that, basically that's an idea of how real-time ingestion works in Druid, how you can set up some stuff to do it. If you have any questions, once again, please read the blog, watch the video, jump on GitHub. We're also in an IRC channel. On the GitHub wiki, there's a link to an IRC channel that a number of us squat in constantly, and we have a Google group that you can post questions to, ask questions of us. It's open. We're looking for contributors. We're looking for new use cases, new ways to grow the system, and ways for it to provide value for lots of other people. And so I hope if you're interested, please talk to us, let us know, and yeah, thank you. Questions? Everyone tired? Done? Ready to go home? Question?
So in case where you get the below 5-second kind of near real-time data availability,
Yes.
are you actually having duplicate records in there potentially because of that architecture you just described?
Are we having duplicate records?
Yeah, or have you deduplicated already in that time frame?
For in the 0 to 5 second time frame. So when, specifically with Kafka, when Kafka generates duplicate messages, it's around failure scenarios. And so usually they don't exist. Sometimes they do exist. And so generally, no, there aren't duplicates in there. But also the deduplication, we currently don't do anything to deduplicate things in that kind of time frame. We just rely on batch processing to go back and fix it at some point in time. I don't know, Danny, did you guys do anything around deduplication? Or?
Not right now.
Okay.
Because that's aggregate data, right? If there's a few percent, not per few, let's say 0.05% of a duplication, then that doesn't really matter to us.
Yes?
So your real-time nodes are the actual Kafka consumers?
The real-time nodes are Kafka consumers, yes.
Back acknowledgement, you have the logic in your real-time nodes know next time, so the next batch you have to pour out of Kafka, or how do you use that acknowledgement?
Yes, it's basically we just use the consumer groups and we turn off auto commit is how we do it. Does that make sense? Yeah. Okay. How is it related to the Apache Drill project? There are lots of people making systems that do things very similar right now. Apache Drill, my understanding, so one thing, Apache Drill is kind of going after the Dremel model, where I would place, if you're familiar with Google's Power Drill paper, I would place us closer on the spectrum of things to Power Drill than to Dremel. But we're not, Power Drill does a lot more compression techniques than we currently do to handle things, and also Power Drill doesn't really allow for swapping from disk, is my understanding, where we actually make it a deployment time concern to figure out if you want enough capacity to hold everything in memory, or if you want to allow it to swap in and out of disk. And so there's some differences there. So anyway, but the question was about Apache Drill. Like one thing that we don't support at QueryTime is like we don't have a join operator that you can do at QueryTime. We basically, when the data comes in, we expect it to be a fully denormalized feed that comes in, and then you do queries on that denormalized feed, where I believe Drill is going into deeper functionality and trying to implement joins and other things like that. And so I think, yeah, there are differences there. On the actual real-time ingestion side of things, I believe, I'm not sure, but I believe that they're counting on data existing in HDFS or some sort of Hadoop file system in order to access it. And if that's the case, then the question of reducing the ingestion latency is going to become a question of how quickly can you push data onto HDFS and then read off of it. And that, I think, is going to end up being a bottleneck for, and a pain point in general in getting real-time data ingestion pipelines set up. But I don't know their plans going forward, and so I don't know how they're planning on tackling that problem. I don't know who was first. I'll jump in the middle.
You ingest real time.
Yes.
Basically, event discovery, event processing. Is that correct?
You,
When you look at the event, if you fail or whatever.
do you, when you say event processing, are you meaning like CEP type stuff, or?
Yes, something like that. I hate that one.
Yes. Yes. We. Okay.
How complex that could be? How much? How much history window I can open?
Right. So that the thing that Druid does is it stores. It's a persistence layer that you would put at the end of a event processing pipeline. And so instead of, like with Esper or Storm or something like that, you generally maintain a window of data, and that's what you're querying and using. Where if you're using Druid, what you would do is set up your pipeline, and instead of having a window of data, you would have it output into Druid, and then Druid keeps what's going on in the current window as well as everything historically, and gives you one query interface to access all of that. Does that make sense?
Yeah, so you can get the real-time ingestion response. Like if you want to find, basically what I'm looking for, if you want to do proactive, you want to see why the user is using, let's say, the site, you want to discover that this is likely to be fraud. Okay, so you want to take longer window to learn better, but you want to act instantly.
So I'm not hearing the full use case, and I'm thinking that we're getting into specifics enough that we should probably take it offline and talk about it afterwards. Are there any other questions?
So I may have missed it. What's the input format that Druid is expecting?
We generally take JSON objects, new line delimited JSON objects, or actually it's Kafka messages, so whatever individual Kafka. But so that's what's built into the code. In general, it's not difficult to plug in a new way of parsing code or connecting to something other than Kafka or something like that. There was a hand over there, yeah.
Would you integrate some, or are there facilities in Druid for integrating with doing more batch-oriented analysis, or would you want to have your separate core to do like machine learning or something on results?
Okay, so the question was, is there room for integrating more batch-oriented analysis, like machine learning type workloads? Is that correct?
Yeah.
I think machine learning workloads are very interesting. We have not fully explored exactly what's required to do them. My understanding of them is that you have data, you run a model, you then see how much error you got, you run it again, you see how much error you got, you run it again. If that's the case, then I believe, so there is the ability to plug in kind of query-specific logic, and you could probably write a query. I believe you should be able to write a query that can do whatever it is you're doing to build your model on each iteration and then go from there. But we haven't we haven't fully explored that, and so I can't say anything more than I believe it can be done, and I would love to explore it. Yes. Is that it?
Okay. Thank you.